Okay, so hello everyone. Welcome to today's quantum spacetime seminar. We are very happy to have Chris White from Queen's Mary University of London, who will tell us about the double copy gravity from gauge theory. Over to you, Chris.
Thanks. Well, thanks for that introduction, also for the invitation. I'm not assuming that people are going to be at all familiar with this topic, so I'm trying to give like a review talk where hopefully people can get who are interested in it can then follow up. So do ask questions, obviously, throughout if anything is unclear. It is an area, as we'll see, where people from lots of different backgrounds can contribute, I think. Okay, so let me give an overview of the talk. I'm going to talk a little bit about scattering amplitudes in gauge and gravity theories. Many of you will be familiar with this anyway, of course, but that will also set up notation that I need throughout. I'll then talk about something called the double copy for scattering amplitudes. Now, the double copy, as we will see, is a relationship between gauge and gravity theory. So it started in scattering amplitudes and then spread outwards from there. So I'll talk about its original incarnation for scattering amplitudes. I'll then talk about how it also applies for classical solutions, which is the work I'm mainly known for, I think, in this area. In some cases, we can look at exact solutions and match them up. And then I'll talk about if we can only do that perturbatively and what that might be useful for. And then go beyond perturbation theory. So basically, the whole theme of the talk is gradually widening this thing that we call the double copy. So I don't expect any of this to necessarily make sense at the moment, but hopefully at the end of an hour or so, it will do. And please ask again if not. So what are gauge theories? Well, as we all know, 3 out of the 4 forces in nature are described by gauge theories. Now, I have in mind here the forces that are in the standard model of particle physics. You may object and say, well, gravity itself is sort of like a gauge theory. But I do want to draw a distinction in this talk between things like abelian or non-abelian gauge theories, Yang-Mills theory or something, and gravity. So I will just use the term gauge theory to mean non-gravitational theories in the talk. Now, the one we arguably care about the most, perhaps, is quantum chromodynamics, because that underlies current accelerator experiments. I nicked this from the Atlas website some time ago. Someone else can tell me what event this is. I think I've long since forgotten. But indeed, you know, quantum chromodynamics is very important because it's tested at current experiments. And that means we have an enormous number of results from non-abelian gauge theories because we've needed to have them to analyze these experiments. So yes, that's an example of a non-abelian gauge theory where the quantum theory is very well understood. Gravity, however, operates on very different scales. So it's relevant for astrophysics and cosmology. But quantum effects, of course, are believed to be important at extreme energies, such as the Big Bang and the centers of black holes. So yeah, now what we know, of course, is that the traditional formalism of gravity, by which we might mean general relativity, or we might mean extensions of it, those traditional methods make it look very, very different to the other forces in nature. And it's also true that the quantum theory is not very well understood. Now, we have some candidate theories, of course, like string theory that and other ones that do look at quantum aspects of gravity. But of course, it's still fair to say that we're not there yet in terms of having a quantum theory. Now, what's happened in the last 10 years or so is that we have a recently discovered correspondence that tells us that gauge and gravity theories are actually much closer, perhaps, than we previously thought. Now, this itself goes back to previous work in string theory, which you may have heard of, and as we'll see. But this new correspondence, anyway, is called the double copy. So it first arose in the study of scattering amplitudes. A key quantity in any field theory, as I've written here, is the scattering amplitude. For those that don't work on this every day, typically in an experiment or something, we have some particles coming in and some particles going out. And in a quantum theory, we can only say what is the probability for that to happen. And this number called the scattering amplitude is related to the probability for particles to interact. So in turn, it's related to all the things that get measured, like cross sections and decay rates and so on. And the point is we can write any amplitude as a sum of diagrams. The traditional way to do that is to use what we call Feynman diagrams. And then there are precise Feynman rules that convert each of those into an algebraic expression for the scattering amplitude. So our traditional technology, even though it may be cumbersome in some cases, does in principle allow us to write down scattering amplitudes and calculate them. Now, I'm well aware, of course, that there are modern methods which get rid of Feynman diagrams entirely, and in some cases are much more efficient. But I thought if people hadn't heard of those methods, they will at least have heard of Feynman diagrams, hence my mentioning them here. But all I want to draw attention to if you haven't seen Feynman rules for a long time, is that each vertex in a Feynman diagram is related to a power of what we call the coupling constant, which gives us the strength of the force. And then there are also various momentum factors associated with the vertices. Each internal line in a diagram gives us a factor of 1 over p squared, where p is the full momentum of the particle being exchanged. And then if we have any loops in the diagram, like this diagram here, then we have undetermined momenta that have to be summed over. So, you know, that's the briefest of summaries of how you calculate a scattering amplitude. One way to do it is you write down all the Feynman diagrams, you apply these mathematical rules where the specific factors will depend on the theory, and then that gives you the expression for the scattering amplitude. Now, if you were to collect that all together for a particular amplitude, let's say that I am in a gauge theory and I want an amplitude with L loops in it and M external particles, which is usually how we characterize different parts of the amplitude, then everything I've told you on the previous slide implies that it would have this schematic form. So there will be an overall power of the coupling because of the number of vertices we have. There will be a sum over different diagrams. If there are any loops, so if there are L loops, there's going to be sums or integrals over the different loop momenta that can be running around in those loops. There will be a series of 1 over p squared factors coming from the internal lines. Because the particles have a color charge in a gauge theory, so you know, in electromagnetism they have normal charge. If it's QTD, for example, they have color charge. There will always be a part of each diagram which depends on the color charges of the particles. And then finally, there's everything else in the numerator, which is a dependence on momenta and polarizations. So this is only a schematic form for what the amplitude must look like, but on very general grounds, a scattering amplitude will have this very generic form. So you can then say that given sort of all of this stuff is fixed for any given diagram, essentially the problem of calculating scattering amplitudes amounts to, can you find out what these kinematic numerators are for each diagram, and then can you do these integrals? And the answer in many cases, of course, is no. It's very complicated, but in principle, that tells us how to, you know, what an amplitude looks like. Okay, so yes, each term has a color factor depending on the color charges, and also a kinematic numerator. Now, the other thing I should say about this formula is that these n's here are not unique. So in a gauge theory, I have to pick a gauge for the field, and if I choose different gauges, these things will change for each individual diagram, such that the sum stays the same. And there's also things called generalized gauge transformations, which include field redefinitions in the theory, as well as gauge transformations, and all of those in principle will change these numerators. Now, what was noticed in, I think, 2008 was that...
Why the power of G contains the number of loops, not the number of vertices?
Oh, well, yeah, so I've written it here to contain the number of loops and the number of external particles. Essentially, that factor is coming from the number of vertices that you can basically take. If you were to take a diagram with M external particle lines and L loops and work out how many vertices are there, this is the number you would get. So it does actually contain the number of vertices, but it's just that we can say more than that. We can explicitly say what the number of vertices is. We have L loops. So, you know, what we're saying is M minus 2 plus 2L is equal to the number of vertices. Now, you can prove that, I presume, by induction. I think it's probably related to Euler's formula in the 1600s for graphs. I think there's a relation there. But you know, if you can think of a quick proof, that would be nice, actually. People often ask me, how do you get that factor? And then I can't remember. Okay, so yes, what was noticed in about 2008 is that we can choose the numerators to behave similarly to the color factors. So for the experts, these color factors come from dressing each vertex in the diagram with what we call structure constants for the Lie algebra, for the color Lie algebra. And that means sets of diagrams obey certain identities in the color factors called Jacobi identities. And that's just related to the fact that we have a Lie algebra underlying the color structure.
Can I ask a question?
Oh, yeah, sure.
Yeah, so that this number of vertices that you said, you are assuming that the interaction vertices are all cubic, right?
Oh, yes, that's right. Of course, in non-abelian gauge theories, you also have quartic vertices, but you can always choose, if you want to rewrite those quartic vertices in terms of sums of cubic ones.
Okay.
So, yeah, I have assumed everything's cubic there, but in fact, you can do that, which is, you can do it perturbatively order by order. Yeah, good point. Okay, yes. So what was noticed by these people here is that you can choose the kinematic numerators to obey similar Jacobi identities to the color factors. So that itself is very mysterious. It implies there's some kind of kinematic algebra that somehow mirrors the color algebra. I won't draw too much attention to that in this talk, but it turns out that if you make this special choice for the kinematic numerators, then something quite amazing happens. Imagine I go back to the previous formula and I simply replace the coupling constant with kappa over 2, where that's related to Newton's constant of gravity. And then I simply strip off the color factors and replace them with the second set of kinematic factors. I would then, if I do that, let's just go back, I would replace this factor and I would replace this one, but to keep everything else the same. It turns out that the formula that you get automatically turns out to be a gravity amplitude. Now, it is not obvious that that should happen, but remarkably, it is true. Now, I've not said which gravity theory I'm talking about here. It turns out you can take these kinematic numerators from different gauge theories, and the gravity theory you get depends on the two gauge theories that you've chosen. So, for example, if you chose n is 4 super Yang-Mills, you would get n is 8 supergravity on the gravity side. If you were to take n is 3 and n is 4 super Yang-Mills, you would get n is 7 supergravity, and so on. So the number of degrees of freedom have to match up on each side of the correspondence. You may say, what if you took pure Yang-Mills theory with no supersymmetry and copied it? It is not quite general relativity that you get. It is general relativity plus 2 extra scalars in 4 dimensions. So the axion and the dilaton. Why? The number of polarization states has to match up on each side of this correspondence. So if you have 2 degrees of freedom for the photon, and you've taken sort of 2 copies of that, you end up with 4 degrees of freedom, which turns out to be 2 polarization states of the graviton, and then 2 extra scalars. So to see
just to mix here, can I ask something?
Yeah, sure.
This is different as compared to if I just take a gauge theory amplitude and square it, right? It's a
yeah, that's right. Yeah, you've not taken the square of the amplitude, you've taken a bit of the amplitude and taken 2 copies of it.
I see. And suppose I had taken the square, I would have got only one class of this ni comma ni tilde, or I would not get any gravity thing.
Well, I mean, if you just naively squared this thing, it would just be a completely different formula, but because you'd have the square of a sum of terms, which is not the same as the sum of a square of terms. Also, the denominators here are not squared. So right. It is only these bits in the numerator that are squared. That are taken 2 copies of. If you have the same gauge theory being chosen, you are allowed to do that, and then it looks like you've squared the numerator.
Right.
But in general, you could choose 2 different sets of numerators. And remember that this squaring happens term by term, so it happens for each diagram separately, if that clarifies things.
I see.
Yeah. Now, it's often, this idea is often cited in the literature as gravity amplitude of the square of gauge theory ones. That is not literally true. that phrase is just very, very confusing in some ways.
So can you please say a little bit more about the first statement? Can choose the numerator to behave similarly to color factors. So these are the kinematical.
I mean, this is a whole fascinating topic in itself. So are you aware of the Jacobi identities between different graphs? If I write the color factors of, say, let's go back here. This is what we call an S-channel graph. This is what we call a T-channel graph, and this is what we call a U-channel graph. So this is not a loop here. They're meant to be crossing over each other, these. If I want the color factor of this diagram, I have to dress this vertex with a structure constant. So if this has color index A, B, and C, I would get F, A, B, C vertex. And likewise, I'd get a color factor at this one. So the color factor of this diagram is a product of 2 lots of structure constants. And likewise for this one, and likewise for this one. Now, when you have products of 2 structure constants and you sum them together, then you get a Jacobi identity for the structure constant. So I assume you know what I'm talking about.
Yes. All right.
Okay. So that means then that these cubic diagrams can be put into sets of 3 where the color factors of each one of each of these sets obey Jacobi identities. So imagine if this were not a single diagram by itself, but part of a bigger diagram, where I have the same thing on the left and the right that I have in these other diagrams. Then it would be true even at loop level that color factors of individual diagrams sum to give Jacobi identities, where you've just taken an individual bit of the diagram and sort of done an STU correspondence. So at arbitrary loop level, I can put all of my diagrams into overlapping sets of 3 where the color factors are related by Jacobi identities. What this property says, which is called BCJ duality, is that whenever you have that correspondence between sets of 3 diagrams, you can choose the kinematic numerators, which are functions of the momenta in the diagram. You can choose those to obey exactly the same Jacobi identities. Now that itself is remarkable, because there's no reason why, a priori, why that should happen. And what it implies is that there must be some kinematically algebra whose Jacobi identities give you those relationships between the numerators. Unfortunately, in most cases, we don't know what that kinematic algebra is. In certain cases, we do. So in some, if you look at the self-dual sector of gauge theory, where you basically have gotten rid of one of the helicity states of the gluon, there we do know what the kinematic algebra is, and it turns out to be some sort of area preserving diffeomorphism algebra. But what that algebra is more generally, and what it's useful for, is relatively unexplored. And there's some quite mathematical work to be done there, also physics work, and I think it's quite a fascinating topic. Does that help answer your question?
Yes. Thank you.
Okay.
Sorry, go ahead, Bindu. I have a related question. These ends you said are dependent on the gauge fixing, right?
Yeah, they will be. Yeah.
Yeah. So in general, is the statement that it's not a gauge invariant?
Yeah, that's right. That's exactly right. The double copy is only manifest in certain
this particular gauge.
Generalized gauges. So you might have to do a field redefinition as well as a gauge transformation to put these ends in this special form. And the double copy is only manifest in that particular gauge. Now, what some follow-up work has shown is that you can write something like the double copy if you're in different gauges. It just has a more complicated form that is not as simple as this. So maybe the correct statement is it's only a simple product diagram by diagram in certain gauges. There would just be a more complicated formula in different gauges, but we don't know in general how to work it out.
But aren't amplitudes in the final run gauge invariant?
Yes, they are. So if you start with something that has this BCJ dual form and you double copy it, you will get a gauge invariant amplitude. But of course, on the gravity side, coordinate transformations will mix up these terms between diagrams. And there's no guarantee then that the copying procedure commutes with the ability to form if you did a gauge transformation and then took the copy, that is not the same as taking the copy and then doing a coordinate transformation. So if you think carefully, there's nothing inconsistent in what I'm saying.
Okay.
The amplitudes on both the gravity side and the amplitude side are gauge invariant, but the copy, as I've written it here, is only true in certain gauges. That is all true, and it is all consistent, but it perhaps takes a bit of thinking about. Does that answer your question?
Yeah.
Hi, Christopher. I know you have to go on, but just very quickly, what's really striking to me about this method of doing the double copy is that you get any kind of sensible theory at all. I mean, if you got a sensible theory, it would pretty much have to be a spin 2 theory. Isn't that right? Because, you're taking isn't that right? Yeah. So I guess what's striking is that you get a sensible theory, where the amplitudes make sense, physical sense, meet all the properties of, the cutting rules, etc., whatever one needs to impose on physical amplitudes, right?
Yes, it is remarkable. We'll see where this came from, this idea, in a minute, and that may partially answer your question, I think. So we'll see. There's a certain string theory origin of this, which maybe makes this clearer, but it doesn't quite explain all of it. So yeah. But I agree, it is remarkable. Now another objection that I get from people sometimes is that gravity is non-renormalizable and gauge theory is renormalizable. So how can it possibly be true? However, of course, we're squaring these numerators at the level of the loop integrand. And these numerators contain loop momenta. So you have higher powers of the loop momentum in the gravity theory than you have in the gauge theory. And thus it is entirely correct that the gauge theory is renormalizable, but the gravity theory isn't. So indeed, you know, if you didn't know that gravity was non-renormalizable, this double copy would have predicted it. So there's a lot of nice stuff we know about gravity theories, which comes out of this procedure. And indeed, this is one of the main reasons I like the double copy and why I've worked so much on it is that it gives us new ways to think about things in gravity. Because if we take gauge theory things and then we copy them in this way, it gives us new insights. And it also gives us new ways to calculate as we'll see. So yes, okay. So I think I've said all I'm going to say there.
So Chris, sorry, I have a question.
Yeah.
So just kind of taking Sandeep's question a little further. I mean, given the way this is structured, perhaps getting the spin 2 theory is not so surprising. But what is surprising to me is that the Young-Mills is related so directly to Einstein gravity. In particular, because Young-Mills has basically only 2 types of vertices, a cubic and particle vortex, while Einstein's theory would have, you know, all sorts of vertices in the Lagrangian. So how exactly does this come about?
Well, we don't understand how the double copy works at the level of Lagrangians to all orders. That is an open question. What I would say, though, is that people have played the game of saying, can I add extra spurious operators in the gauge theory to make this BCJ duality property manifest? So, you know, if you calculate in an arbitrary gauge, your Feynman graphs are not going to be in the BCJ dual gauge where you can take the double copy. So what you can do order by order in perturbation theory is that you can add extra terms in the Lagrangian in QCD that basically cancel off bits of diagrams so that when you calculate perturbatively with that Lagrangian, you get manifestly the BCJ dual where you take a double copy. And remarkably, when you want to make this BCJ duality manifest, you end up adding an infinite number of terms. And those then map to the infinite number of terms in gravity.
I see. Does this also mean that, you know, I mean, perhaps relatedly, you can add higher derivative corrections? You know, think of a Young-Mills theory as an effective field theory with some higher derivative corrections, and then one can also play a game of finding the resulting gravitational theory that you get out of it.
Yes, there is on that. So people have looked at various theories, as we'll see. There's probably more to be done there as well, but it's known in some cases. I think what's not known is can you take an arbitrary gauge theory with arbitrary matter and double copy it? But there are many cases that are known in exotic gravity theories that are known, and including, I think, high derivative operators. This is very topical because one of the applications that we'll see is to gravitational waves, where it's even in classical GR, it's difficult to calculate. You would want to calculate things in an easier gauge theory and put it across. Because people may be looking at higher derivative operators in the gravity context of gravitational waves, you would want to consider the same in the gauge theory.
Okay, thank you.
These are all excellent questions. I mean, I'm loving this. Thanks. Okay. So yes, to see why this is so remarkable, you know, why these amplitudes turn out to be the same. Just to remind you, if you haven't seen the Feynman rules before, the vertex rule in QCD for 3 gluons looks like this. So we don't have to worry about the details. It just has 6 mathematical terms in it. The one for gravitons has over 170 terms in it. So what has held back quantum gravity research for years is just the ability to do the calculations. And you know what this is telling us is that most of that traditional way of calculating is enormously inefficient. There is a huge amount of redundancy that cancels in the theory when you assemble things to make the final amplitudes. So certainly from traditional methods, it's not at all obvious that amplitudes should be related, but indeed they are. So I've talked about this thing up to now anyway, as if it's true. Let's have a look at whether it is. So the double copy arguably remains a conjecture. There are some people that would claim it was proven, but there are counter arguments to that and so on. So yeah, I'll just be diplomatic and say it remains a conjecture, but with a lot of supporting evidence. So there is a string theory explanation if no loops are involved. People may have heard of what are called the KLT relations in string theory, which were written down, I think, about 30 years ago. And those are relationships that tell us that closed string scattering amplitudes are related to products of open string scattering amplitudes. And if you take the low energy limit of a string theory, open strings give you gluons, closed strings give you gravitons or generalizations thereof. And so, you can sort of say that at tree level, the KLT relations are exactly the same as the double copy. However, there is no known loop level generalization in string theory of the KLT relations. So the double copy is more than that, at least until we can prove there's an equivalent structure in string theory. That may go some way to answering the question about how do you know you're going to get a consistent theory. Clearly, there's some sort of underlying explanation in some cases we can give that then guarantees that. It's been tested in NS4 Super-Yang mills up to 4 loop order, which is very impressive. It's also been tested, I should say, at 1 loop level in completely non-supersymmetric Yang Mills theory, which is interesting. So to some extent, BCJ duality and the double copy are genuine quantum properties of the world we actually live in, or at least at low energies. So even if there's no supersymmetry in nature, something like this BCJ duality is still true. And I find that very fascinating. And it's very different to many of the other things in theoretical physics, which have to rely on supersymmetry and to be true and so on. In certain corners of perturbation theory, you can go to all orders in the coupling constant. So one of those is the soft limit. One of them is the high energy or Reggie limit. And we know that this thing is true there. For self-dual theories, as I hinted at just now, there's a complete understanding of how this works classically and also at the level of the Lagrangian. There's something called ambi-twistor string theory for when string theory is not quite complicated enough. And there are loop level insights from that. And also there's been a recent perturbative proof, although as I say, there are still some comments about this, but that's by these people here. Now, I've talked here about gauge and gravity theories. It turns out that these types of correspondence actually generalize to many other types of theory. The other one we'll see in this talk is called biadjoint theory. So what I did before is I took a gauge theory amplitude, took the color factors off and put some kinematic stuff in. I could have gone the other way. I could have taken the kinematic numerators away and put in a second set of color factors. That will give me a field that has 2 different types of color charge, but which is a scalar field. So that is called biadjoint scalar field theory. And its amplitudes indeed are what you get from doing this procedure. And it's a rather unphysical theory because it's got a cubic Lagrangian, so its energy is unbounded from below. But what's remarkable is that amplitudes in this theory somehow, at least part of their dynamics, gets inherited by gauge and gravity theories. So very unphysical stuff in the biadjoint theory turns into physical stuff when we copy it to gauge and gravity theory. So anyway, this is called the 0th copy rather than the double copy because I take 0 copies of the kinematic numerators. And there's by now a very wide network of theories in different numbers of dimensions which obey these kind of copying correspondences. So there's a big review by these people here recently, which would have the latest word, I think, on this. And what we're missing, I think, is an understanding at the moment of which theories are copyable into other theories, and is there some sort of special set of theories in nature that gets picked out by the fact that they're copyable into other theories and so on. All of that is kind of just starting to be explored. So yes, just to summarize what I've said on the last few slides, we have this trinity of theories. If I take non-abelian gauge theory, I can take the double copy of scattering amplitudes and get gravity ones. The opposite is called the single copy for obvious reasons. I could also take the 0th copy to go into biadjoint theory. And then for want of a better term, we call this the inverse 0th copy to go back here. So we have this weird ladder of theories and correspondences taking us between scattering amplitudes. Now, this is by now a very wide area of research. It's really blossomed in the last few years, partly, I think, because people from either gravity or gauge theory backgrounds can get together and talk about it. I would say that if I were to split the research that's going on at the moment into broadly 2 camps, you would have the fundamental camp where you're asking deep conceptual questions like where does the double copy come from? Can it be used for quantities other than scattering amplitudes?
Can I ask a question?
Oh, yeah, sure.
What about the kinematic factor for the biadjoint scalar theory? I mean, is it there? Is there any kinematic factor also for the biadjoint scalar theory?
Yeah, there are no kinematic factors in the numerator of the amplitude just because it's a scalar theory. So all of the Feynman rules at the vertices just involve constants rather than derivatives and things like that.
Okay,
and because there are no polarization vectors either.
So there are no derivative interactions in that theory. That's what you're saying.
That's right. Yeah, that's right.
Yes. Is there a sense in which if you erase the kinematical factor and not replace it by anything else, you get adjoint scalars?
Oh. Yeah, I don't know the answer to that. Diagram by diagram, you know, you would only have to show that diagram by diagram, right? Perturbatively, and then you would have the answer. So yeah, you might be right.
Okay, thank you.
Interesting.
Sorry, so just as a comment, there was this question about how does Yang-Mills Yang-Mills only has 3 and 4 point graviton vertices, but how does it reproduce an infinite number of vertices in gravity? There's this, from the biot joint to the Yang-Mills, sort of a smaller but similar question arises, right? Because you have only cubic vertices in biot joint, but you have in Yang-Mills the cubic and the quartic. And here the quartic vertex in Yang-Mills, you can write it as coming from coming from cubic vertices in some sense, and that's how it gets resolved, right? In fact, that even though you have higher point vertices, you can write all of them as coming from cubic vertices in some sense. So cubic vertices enough to generate opposite side.
Yep. So what matters for that in the gauge theory is that if you look at the color factor for the Ford-Lewin vertex, it's a sum of product of two 3 vertex color factors. And then something similar will be true for all these extra terms you add. That's a very nice point. Yeah, thanks. Okay, so also on the fundamental side, we've got, you know, can it be used for quantities other than scattering amplitudes? The answer is yes, else I wouldn't be giving this talk. So the rest of the talk is going to be, you know, what other things we could apply it to. Is it fully non-perturbative is something that fascinates me. You know, should I take this picture as being true for the complete theories in some sense? And if so, what does that mean? So that's something I'm very interested by. There's also links for string theory that various people explore, and we've already touched on those. However, there's also a very applied stream of research here. Can we get new results in quantum gravity? And indeed, one of the earliest uses of the double copy was showing that N is 8 supergravity is better behaved in the UV than previously thought. So they were able to do those calculations because they could take N is 4 super Yang-Mills results and recycle them. Can it be used in astrophysics? And the pressing problem there at the moment is gravitational waves. To get the most precision out of the LIGO experiments and so on, we need very high orders in perturbative, even classical general relativity. And what's happened in recent years is people have started doing calculations in classical gauge theory and double copying them to get the gravity results. And it's already the case that we have new gravity results relevant for gravitational waves that we didn't know before from these methods. Could it be relevant for cosmology? I get asked about this a lot. Not many people have explored that yet, but in principle it could be true, as we'll see later on. And finally, could it be used in condensed matter and optics, or could those shed light on it? So certain tabletop experiments even can simulate gravitons and things like this, and perhaps say something about these correspondences. So yes, let me now talk about classical solutions. So we do now know that we can extend the double copy from scattering amplitudes to classical solutions. That's something we've known now for a few years. To see what this looks like, in gauge theories, the field basically has a space-time index and a color index, or an adjoint index. And in gravity theories, we usually define the graviton field as the deviation from flat space. Sometimes we may choose a different background, which I'll talk about later, but for now, the graviton is about Minkowski. So what I'm saying by a classical double copy is, can we take a biadjoint scalar field, a gauge field, and a gravity field, and somehow match them up between different theories in such a way that we know that that is the same as the double copy for amplitudes where they overlap? So the answer to that question is yes. In general, it can only be done order by order in perturbation theory as for amplitudes, but special cases actually allow for exact statements. So there are 2 known procedures for generating exact classical double copies. The first actually looks at an infinite family of solutions with very nice properties. So they're called Kerr-Schild metrics in GR, and they have a very special form for the graviton, where the graviton is an outer product of 2 vectors with a scalar field. So, you know, not every metric can be put in that form, or not every graviton. And also this K has to have certain conditions. It has to be null, and it has to be geodesic. So there's a geometric interpretation of this as if you sort of drag the vector along its own vector field or something. So I'm not sure that helped, but you get 0. Now, each of these Kerr-Schild solutions is classified by the scalar field and by what I'll call the Kerr-Schild vector. And actually this ansatz arose historically because it has the effect that if you put it into the Einstein equations, they become linear. So you've not thrown any terms away, It's just that the equations themselves happen to linearize. And that means it's much easier to find solutions. So this is how the Kerr metric for the rotating black hole, or Kerr black hole, was originally found, actually using this, this prescription. Now, what's nice about this from our point of view is because the Einstein equations have explicitly linearized, any statement you can make for this family of metrics is an exact statement, if you like, to all orders in perturbation theory. Now, what's also nice about this Kerr-Schild ansatz is it sort of suggests what you might have to do to take the single copy of this. So to get a gauge field, you would simply strip off one of these kinematic vectors and replace it with an arbitrary color vector. So this is just some constant color vector. And what you can prove for all stationary solutions is that indeed this solves the linearized Yang-Mills equations. So it just looks like you have a number of copies of the Maxwell equations. And similarly, if you do it again and just have two color vectors and no kinematic vectors, then that solves the bi-adjoint equation. So this then succeeds in giving you a tower of exact classical solutions that are related to this by the same copying procedures somehow as the amplitude story. Now, it won't be obvious from this that this is in fact very closely related to the amplitude story, but we now know in much greater detail than when this was first proposed that that is really true, that that this is very closely related to the amplitude story. One thing that's quick to mention that I can say about that is that we saw that for amplitudes, you didn't touch the denominators of the amplitude when you copied the numerators. And those denominators have an interpretation as being like scalar propagators. Likewise here, we don't touch this field phi when we go between the different theories. And because this phi solves the linearized bi-adjoint equation, it is itself a scalar propagator. So there's something very similar going on here for amplitudes, but I can't really say much more than that without getting a lot more technical. Anyway, that was a very abstract discussion. You may say, if you've not seen these things before, well, are these Kerr-Schild metrics useful for anything? Actually, some of the most famous solutions in gravity are of Kerr-Schild form, or can be put in that form. So the Schwarzschild black hole is one of them. Normally, we think about the Schwarzschild black hole in a different coordinate system, but you can do a coordinate transformation so that it has this form where k is just 1 in the time-like direction and a unit radial vector, and phi just goes like 1 over r. And if you take the single copy of this using the rules I gave you, I'm skimming through this rather quickly, but we basically get a point charge. So what the single copy has done is it's turned a point-like mass in gravity into a point-like charge in the gauge theory. Now that, if you like, is an analog of the fact that kinematic information in the gravity theory for amplitudes was replaced by charge information in the gauge theory. It's exactly the same sort of idea. So it's very physical in some sense what's going on here. Now, the next simplest example is the Kerr black hole.
Sorry, a very trivial question. In the previous slide, please.
Sorry, say that again. I can't quite hear.
In the previous slide, can I ask a question, please? In the previous slide. So I missed one thing. So in H mu, you are rewriting H mu as K mu with a. So this is the way you are generating a solution, or what about? Sorry, what about the? This is the way you are parameterizing H mu, or what exactly are you doing? Sorry.
Yeah. So. What I'm saying is that for certain gravitons, we know how to take their single copy exactly, and those are ones which can be written in this form.
I see, only for those ones. I see, sorry.
Yeah. I mean, we know a little bit beyond that now, but this was the first case of a classical double copy that was understood. It was only this very special class of metrics. So as I say, that has a name in the literature. They're called Kerr-Schild metrics. So this is some existing body of GR knowledge. But they're very special metrics. Do you know about the Petrov classification?
Yeah.
Okay, so these are type D metrics, basically, could be put in this form.
I see, okay.
Only a certain family of things. So, yeah.
Chris, what happens when you do zeroth copy of the Schwarzschild black hole?
So you basically get a point charge in the bi-adjoint theory.
But I thought this 1 over R factor was coming from some sort of a kinematic thing.
Yeah, that's right. So the 1 over R factor is just the scalar propagator, and it's there in all the theories. Oh, and then what happens between the theories is the mass gets replaced with a point.
So that charge is there, okay.
And then a point like bi-adjoint charge. So two different types. Yeah.
Right. Okay, thanks.
I have a related question. Can you go back to the previous slide? Previous slide, please. Yeah, so
that one,
the Schwarzschild solution in general can it be written as 1 by r times kmu knu? Because it's very, in general, it's quite complicated and the metric is quite complicated. So h mu nu doesn't generally have a 1 by r form. So I'm wondering how here you can write it as 1 by r times kmu knu, where kmu is just 1 er.
Yeah, you're right to wonder that. So normally, of course, when we see the Schwarzschild metric and the way we first learn about it, it has things like 1 over g minus m and things like this, or gm minus r. And so you have all powers in the coupling constant. What I'm saying is that there is an explicit coordinate transformation that linearizes the metric and gives you a single term with this 1 over r dependence. Now, for this particular metric, those coordinates were already known. Do you know about Eddington-Finkelstein coordinates?
Yeah.
So if you write the Schwarzschild metric in Eddington-Finkelstein coordinates, it has a single term with a single power in the coupling, and the Kerr-Schild coordinates in this case are just Eddington-Finkelstein coordinates.
Okay.
So it is remarkable, but it is true. Now I could even tell you what the coordinate transformation is. I have it somewhere, and I've also got a review article where it's done in the appendix if you're interested. Okay.
I also have one question. If we naively add more numerators, so more NIE factors, do we expect to get a higher spin amplitude?
Oh, I think in principle, yes, although such higher spin theories are not consistent in flat space, I think, right? However, what you could do is go into ADS, where there are these higher spin theories by Vasiliev and people.
Yes.
And I think probably something like what you're saying would be true there.
Okay. Yeah, but there's no, but this thing, at least the double copy, gravity being double copy of gauge theory, there's a string theory tree-level explanation, but for higher spin also, can that explanation go through? No. That explanation is just for open and closed spin, so I don't know.
Yeah, I don't know what's been done on the KLT relations in other backgrounds. Yeah, I just don't know enough about the string theory aspects. So there may well be something to think about there, but I don't know the answer, I'm afraid.
Okay, thank you.
Okay. Yeah, so the next simplest black hole is a Kerr black hole, and what the Kerr black hole is in GR is, imagine you've taken a disk of mass and you've rotated it. It generates a rotating black hole. So that's the minimum source you need to get that metric. And the single copy turns out, unsurprisingly, to give a rotating disk of charge, because all the mass has been turned into charge again. And you can really check this. So here I've plotted the magnetic field. And if you go to large distances, it looks like a bar magnet. Now, why is that? Well, coils of current are magnetic dipoles. And so a rotating disk of charge is just a load of current coils. And so, of course, you would get something like a dipole field. So, there's a lot of nice physics in this that's fun to play with. Now, also some other examples are known, which I'll skim over because we're getting short of time.
Okay, I have a question about this.
Yeah,
okay.
Sure.
So you gave an example of Schwarzschild black hole and a Kerr black hole and a single copy of that. If you take a charged black hole, for example, Eastern-Nordstrom black hole, because we have an extra charge on the black hole, what is a single copy version of that?
Yeah, that's very interesting because various people have tried to figure out Reissner-Nordstrom, and no one has managed to do it that convincingly. What would need to happen there is that you would need to, in the double copy, you would need to generate not just gravity, but Einstein-Maxwell theory, possibly with some extra matter. So you would need a gauge theory copied with a gauge theory with additional matter in it, such that you got Maxwell on the other side. So yeah, as far as I know, no one's quite managed to figure that out, but I may be able to, if you're really interested, I may be able to find some places in the literature where people have at least started to address it. But it's
okay.
Can it be written in the phi kmu knu form?
It can be written in Kerr-Schild form. Yes, it can.
Okay.
Yeah. Again, remarkable.
Okay, thank you. Yeah.
Thanks. Okay, so that's one exact classical double copy. A second exact classical double copy has been given by these people here. It's called the Weil double copy, and it's formally independent of the Kerr-Schild approach, but they do overlap quite considerably. Now, to state the val double copy, I'm going to need to develop the appropriate language, and apologies for this being a bit of a crash course. But it uses the spinorial formalism for field theory, which I'm assuming not everybody will have seen. So I'll just say a few words about it. We usually learn about field theories using the language of 4 vectors and tensors, but an alternative formalism exists in terms of 2-component, what we call Weyl spinors, and their conjugates. So here, A is an index that goes from 0 to 1. And as well as these objects, we can consider objects with multiple spinor indices, as we'll see in a moment. Now, in principle, to convert from a space-time index to spinor ones, we can contract, for example, a 4 vector with these symbols here, which are called Imfeld von der Waerder symbols. And they basically take you from a space-time sort of vector basis to a spinor basis. And these just happen to be what these matrices are in some basis. What's also true in spinor space is that we can raise and lower indices with Levi-Civita symbols. You know, that plays the role, if you like, of the metric for raising and lowering indices normally. Now, if you've not seen this before, I mean, you really have to sort of study this formalism. There are some very good references which I can point people to if they want to. But you may be wondering, why on earth would you do this? You know, if you feel comfortable with 4 vectors and tensors, why would you translate to a completely different formalism, which is what the GR people did in the 70s or so? And the answer is that some very nice properties emerge in the spinor language. So very often in physics, you use the right mathematical language for that's most convenient for what you happen to be talking about. So let me talk about some of those properties here. It turns out that first of all multi-index spinors can be reduced to sums of products of fully symmetric spinors with Levi-Civita symbols. So let's say I take the electromagnetic field strength tensor in space-time. Each of those indices, if I contract with these symbols, will become a pair of spinor indices. So I get something with 4 spinor indices. And my claim then is that that decomposes into a lower thing, which is symmetric in these indices, times this thing which is anti-symmetric. Now, it's not too difficult to prove this property. It just relies on the fact that these indices can only take values of 0 or 1. So that kind of trivializes things. And that decomposition property is clearly showing up some sort of inner structure to these objects, which is why the spinor language is particularly useful. Also in GR, gravity is described by the curvature. Oh, yep.
So here, the F you're assuming to be on shell, right? I mean, otherwise, I don't think, for general F, I don't think it can be written. Can it? I think.
Well, I'll be talking about classical fields, which in some sense are off shell, because you're not going out to infinity and measuring the field there. You're measuring it at a finite point in space.
By on shell, I mean they satisfy the equations of motion.
Oh, yes, that's true. That's true.
Yeah. Okay.
Yes, that's true. But of course, we're going to be looking here for the double copy of exact solutions. So it doesn't matter. Okay, so yeah.
Why the field needs to be on shell? This is just the symmetries, right?
Yeah. I don't think they need to satisfy any equations of motion.
Actually, yes, yeah. You're right. I mean, it's true that the solutions I'll be considering do, but indeed, maybe you don't need to. So you're saying if you had an F which didn't satisfy the equations of motion, I mean, it would certainly have this spinorial translation. So that would certainly be true.
Yeah.
And it just follows from symmetrization and anti-symmetrization in the spinor indices.
Yeah.
In general, if you have a general F A prime BB prime, then can it be always be factorized in this form for a general? For instance, if you just have an arbitrary F alpha beta, and
if I may answer the question, it can be factorized. And it's just like going from vectors to spinors. You're going from 2 index tensors to tensors with spinorial indices. That's all that's really happening.
I mean, what you do to show this right-hand side is that you can write, let's say I take the indices A and B, you can write that thing as the sum of the symmetric and the anti-symmetric part. But if the indices only go from 0 to 1, then the anti-symmetric part must be proportional to a Levi-Civita. It can't be proportional to anything else. So it happens on very general grounds that decomposition happens, I think.
I think if you just count the number of off-shell components, left-hand side and right-hand side, they match. So there is no equations of motion involved anyway. 6 on the left-hand side, there are 6 components, and on the right-hand side, there are 3 plus 3 components. So 6 in total. So
I like that. Thanks for doing that.
Okay, I think if you had self-dual or anti-self-dual, then only one would survive, and then
Yes, that's right. In fact, we're going to see this in a minute. So yeah, so the equations of motion will just put constraints on these things. Okay, so likewise in GR, if we're in a vacuum, the Riemann curvature will reduce to the Weil tensor if we're in a vacuum, which is what we'll consider. And again, that splits into two parts. So I will call the electromagnetic spinner and the Weil spinner respectively. Now, what we see is that there are similarities between the two spinner decompositions of F and C. So it turns out that, first of all, that these two parts here correspond to the self-joule and the anti-self-joule parts of the photon, and likewise for these in gravity, it's the anti-self-joule and the self-joule degree of freedom of the graviton. Now, what do the field equations look like when you translate them into this language? If you've got vacuum fields, then you basically get what are called the massless free field equations. So if nabla here is the spinel wheel translation of the covariant derivative, you get these equations on these multi-index spinners. So, you know, this works for any spin of field, and there are now 2n indices then for a spin n field. Okay, so that was the first property of spinners I wanted to draw attention to. The next one is that all fully symmetric spinners decompose into symmetrized products of one index, what we call principal spinners. Now, again, this is not too difficult to prove. It happens very generally, and it's to do with the fact that the indices can only go from 0 to 1. So if you look at the degrees of freedom of the expressions that we see here, it is equal in general to the number of degrees of freedom on the left. So indeed, for the electromagnetic and the Weil spinners, it means that we can basically say this phi has these principal spinners in it, where we have to work out what these are in general, and then, you know, a Weil tensor will split into principal spinners and so on. Now, one of the reasons that's useful, that property, is that it allows us to classify different types of solution. For example, if I take the simpler electromagnetic case, there are clearly two distinct types of solution. So there are infinitely many of either of them, but there's two types of solution. One is that these principal spinners are proportional to each other, in which case we call that a null field, or we have a non-null field, which is when they are not proportional to each other. Now in gravity, clearly there's many more possibilities than that. You can have different patterns of degeneracy of the principal spinners. So this means they're all the same, or I can have 2 and 2, 3 and 1, and so on. And this relates to this Petrov classification that I mentioned earlier. So there was work done already decades ago classifying different types of solution into sort of qualitatively different types called Petrov types. And in the tensorial language, that is really quite cumbersome to look at. In the spinner language, it's remarkably simple. It's just what is the pattern of principal spinners that's in my Weil tensor, and then that tells you the different types of solution that you have. Why is that useful when thinking about the double copy? Well, it may well be then that it's only certain types of solution that we know how to double copy, and if we want to work outwards from that, we might want to consider the next most complicated Petrov type, and so on. So yes, a Petrov type, just to clarify again, does not uniquely fix a solution, but it's a useful qualitative tool for putting things in different types. Okay, that now gives me all the language I need to state this Weil double copy. What these people said is if you take two electromagnetic spinners, you can make a Weil spinner out of them according to this formula. So you take a symmetrized product of these things, and then you divide by a scalar field. Now, this is analogous to the biadjoint field in the Kerr-Shield approach. And remember, in the gauge field in the Kerr-Shield approach, there was a sense in which that phi field was sitting in both gauge solutions. So there's a sense in which it's been counted twice here. And so this division is really sort of correcting for an overcounting of the fact that that scalar field is present both here and here. So yes, this thing on the right clearly could be a Weil tensor because it has the right number of indices and it is symmetric in those indices. What is remarkable about this statement, of course, is that it turns out to solve the massless free field equation. So they argued that this works for arbitrary vacuum Petrov type D solutions. It's also been shown since that it works for some type N solutions, which are relevant for gravitational waves. And we can translate from this to the Kerr-Shield approach where relevant. So what are the current topics in the Weil double copy? Well, when I first saw the Weil double copy, I thought, well, that's a very nice formula. Where on earth does it come from? Because it's so mysterious looking, particularly if you're learning these spinner methods for the first time, which I was. And it turns out that you can use twistor theory to actually derive where that Weil double copy comes from. What we hope about those twistor methods is that they will allow us to say when we get an exact double copy in position space and when we don't. And so I've got a paper in preparation sort of arguing when that should be. So yes, the other thing about these twistor methods is that they show that the Wahl double copy is actually more general than previously thought. And other twistor constructions exist for radiative spacetimes. So, you know, various people that know about twistor theory are now starting to get involved in this, and some of those methods can tell us interesting things about the double copy. Now, I have not bothered explaining those twistor methods in detail in this talk, because, you know, it's a rather specialist subject that takes quite a lot of time to explain in detail. But, you know, for anyone that knows about those methods, I encourage them to perhaps get in touch and say, well, you know, could they be doing anything in this area? So yes, the other thing is that very recently it's been shown that twistor methods can be used to link the classical double copy much more strongly to the double copy for scattering amplitudes. And so that itself is interesting. You can also include source terms in the Wahl double copy. So everything I've talked about up to now is vacuum, and people have started putting sources in, which generalizes the types of metric we're able to get. And yeah, that's the current status of the Wahl double copy. Now, I should say that for linearized fields, there's yet another approach for classical double copying. It turns out that you can write arbitrary gravitons as convolutions of gauge fields in the linear theory. So remember that the original double copy for amplitudes involved products in momentum space. That means one should expect things. Sorry, is it me that's doing all that beeping? In which case I can try and turn this off. Okay, sorry. Okay, so yeah, naively you would expect actually a convolution in position space of fields, not a product, because you really expect the product to be there in momentum space. So it's always been a bit of a puzzle for the position space double copies, why they work in position space. Now the twistor methods actually shed light on that, which is some work in preparation. But anyway, some people have put together a program where they take convolutions of fields in position space and show that you arbitrarily can generate double copies. So they have used this principally to look at a catalogue of different supergravity theories, both with and without matter. So it actually allowed them to find new theories where this thing should be true. The other thing is that this statement works in any gauge in principle. So they've even managed to take, for example, BRST ghosts, if people know what those are, on the gauge theory side and map them with things on the gravity side. So I think this approach is the best one we have at the moment for really saying how do off-shell degrees of freedom map between different theories. And, you know, remarkably, that seems to be true in many cases. Yes, okay, so I've got a few words on that, in fact. So a textbook way to deal with gauge redundancy is to introduce what we call for of Popov ghosts. And the Lagrangian with ghosts included obeys an abstract symmetry called a BRST symmetry in this double copy that was pioneered by the Imperial group. So this convolution approach, you can actually write a dictionary that relates the physical and the ghost degrees of freedom on the gauge and gravity sides. And if you then impose the BRST symmetry on both sides, then you end up constraining that dictionary. So this is very abstract stuff done in a series of papers. What we did in a recent case study was just show explicitly how this works for the simplest solution, which is a point charge. And it's also possible to extend this to higher orders in the coupling. So for that question earlier about you know, should this double copy in principle be true in arbitrary gauges? I think the answer is probably yes. And some approach like this one would be useful for actually mapping out how that worked in general, I think. But it's still early.
Sorry,
yeah.
Christopher, I got a little lost. Is the imperial approach at linearized level and amplitudes then? Or I mean, is it some kind of amplitude expansion or true in general?
So there, they were talking about classical fields.
Yeah.
So, and
I mean, amplitude I meant in the size of the perturbation, not your amplitudes with which you began your talk. Yeah.
Ah, okay.
I mean, is it linearized perturbation?
Yes, what I'm trying to say. It's linearized in the coupling.
In the coupling.
So I mean, you've got kind of two expansions you can talk about in GR, right? Because you've got the coupling and you've got how big is the field.
Yeah.
You know, strong field or weak field. So, for example, what happens in the Kerr-Shield double copy is that your linear order in the coupling, but the field will be very large in general, because you've essentially summed up in other coordinate systems for the Schwarzschild metric. The field goes to all orders in the coupling or something. You sum that all up to make a single term. So the field will be large, but it's linear in the coupling. Here, they're linear in the coupling only. So I think the fields could be strong fields. But if you had a solution that was genuinely nonlinear, then you would need to include that with some sort of higher order corrections to this approach.
Okay.
Now, as far as I know, that how to define that convolution is tricky at higher orders, but I think some work has happened on that. I should say I'm the wrong person to talk about how this has evolved. Sylvia Nagy is always very willing to talk about this, actually, if you contacted her. And Liron Borston is the other one who's involved in this approach. As I say, I'm kind of fascinated with this approach and have watched it from the sidelines simply because, you know, if the double copy is non-perturbatively true somehow, we ought to be able to understand it for off-shell degrees of freedom. And that's what they've succeeded in doing, at least in some limit. So I don't know how to extend what they've done, but I want to see it extended.
Okay, thank you.
That answers your question.
And also, I mean, I have a question about this gauge freedom. I mean, when we introduce Faraday-Popov ghost in this double copy kind of dictionary, what is the analog in the gravity side?
There are things, and I can't remember the acronym. They're called, is it BV ghosts or something like this? There are sort of vector valued ghosts and things that you can introduce in gravity. And you can really show that those ghost degrees of freedom are given by certain combinations of ghost degrees of freedom and gauge field degrees of freedom. So, you know, the kind of off-shell and on-shell degrees of freedom mix up with each other when you take the double copy, such that you end up with vector valued ghosts in gravity. I'm really not explaining that very well.
Okay, yeah.
I don't expect that at all answers your question. Well, what I would say is that this, I can point you to the paper where we looked at this for a point charge. And what you have in that paper are formulae where you say, these are the ghosts in gravity, and this is how they're related to the degrees of freedom for the gauge theory. And that formula says much more than the waffle I'm giving you now.
Okay, yeah, thank you.
Okay, so I want to say a few words about as well how we would extend this away from flat space. So far I've only been talking about the graviton as being defined around Minkowski space, but it has also been extended to curved space as well. It's early days, but it might be useful for things, so I thought I'd mentioned it. So in particular, we can define gravitons around a non-trivial background metric. So G bar here is some dynamical background metric. And this happens quite a lot of the time in GR. We might have an FRW metric representing our universe, about which we take perturbations and so on. So then we can examine, is it true that you can construct a graviton around a non-trivial background metric such that that is some sort of double copy of a gauge field living in some theory? And there are then, if you think about it, two possible types of double copy you could consider. You could take a Minkowski space with a background gauge field in it, where there's a perturbation defined around that background gauge field, such that this background metric is the double copy of this background gauge field, and the perturbations are also double copies. So that is the kind of strict, correct double copy, and that's what we call a type A one. There's also something called the type B double copy, which is where we could consider a gauge field defined on a non-dynamical curved background. We just say, why not? Let's have a non-dynamical curved background that is the same as the one in the gravity theory, and then just have the graviton as a double copy of that. Now, that is not kind of strictly correct from a double copy point of view. It's not expected to be generally true, but it does turn out to be true in some cases. So it may be worth considering in case it's useful for something. So yes, to discuss each of these in turn, the type A double copy appears to be as general as the flat space case. So then we would also have a zeroth copy where we have a background biadjoint field. And it's also been explored in the context of ambitwistor string theory and amplitudes, as well as in the context of classical solutions. So it seems there's a lot more general stuff that could be said there that might be useful for something. The type B double copy is not expected to be fully general, but it does work in some non-trivial cases. And for example, I suspect it works for arbitrary conformally flat metrics. And I think the twister methods I was talking about before actually would explain why that is, because those twister methods are themselves conformally invariant somehow. And there's further nice examples given by these people here. What I would say is that the list of examples where this works include astrophysically relevant spacetimes like de Sitter, which we happen to live in, as far as we know. So no one's really applied the double copy to cosmology, but I wonder whether there are things one could do, in which case you might want to consider some kind of curved space double copy and so on. Some other people have started to look at amplitudes in ADS backgrounds, I think trying to draw connections between the double copy, which is a weak duality, and ADS CFT, which is a strong weak duality. So, you know, there's also some people looking at this from a completely different point of view, looking at amplitudes in ADS. So again, quite interesting, I think.
So, sorry, just one comment. You know,
yes.
On d-sitter, which is also same as d-sitter 4, which is same as CFT3 correlation function at the level of 3-point amplitude in d-sitter in your type B way of doing, you know, which is rigid d-sitter, and then you calculate various things. Their double copy for 3-point function at least has been established very. You know, at the level of 3-point function, it just a squaring gives you the double copy, you know. So that I think has been shown. For higher point, it's not yet very clean whether.
Okay, that's interesting. So I know of some work there. I would say that the curved double copy stuff I did was for classical solutions rather than amplitude. So I'm actually less familiar with the amplitude side. If you could send me an email actually with that, with a reference for that'd be great. I think for higher point amplitudes, there's some preliminary work in ADS by Arthur Lipstein was one of them, and then there was another.
Not very clean though. There are some preliminary work, but for 3-point, it is very clean. It's very clean.
They seem to be saying there were correction-like terms that vanished on shelves or something. There was, I don't remember the exact details, but there was some. You're right. I mean, it wasn't quite as conceptually nice as for the flat space case. Although that doesn't necessarily suggest it's not useful for something, which maybe it is. Okay. So yes.
I have a question. In the curve double copy type A formalism, are you assuming some sort of linearity, because it looks like you have sum of solutions in the gauge theory as a sum of solutions in the gravity also?
Yes. Well, the cases we looked at the moment were ones that linearized the respective field equations. It could, however, be that there are nonlinear cases. You know, this could be a solution of a nonlinear equation, which is living in, you know, which has this background. You know, it seems to me that there could be a situation where you have Minkowski space, you have a background gauge field filling it, and you solve the nonlinear Yang-Mills equations assuming that background. You've essentially just, instead of perturbing around the vacuum, you've perturbed around a different background, and you could get nonlinear corrections on that, such that the nonlinear corrections in gravity are double copies of the nonlinear corrections here. I don't think that's impossible, but indeed I don't know of any cases.
Okay.
You know, there's no linearity necessarily assumed in saying that the sum of these is a solution. What this amounts to essentially is that you have perturbed your solution about this background rather than about the vacuum.
Okay, yeah.
Okay, yeah, so that's all I'm going to say about exact classical double copies. We do not know how to double copy arbitrary solutions exactly, but we don't always need to. And also in GR, you know, you can't always solve for something like a black hole merger that causes gravitational waves. We're never going to be able to find the exact metric of that because it's different for every single colliding system. You just work order by order in perturbation theory, and you're happy with a sufficient approximation to what the full metric is. So we can consider more complicated solutions at the price of working order by order in perturbation theory. Now, this is in some sense an off-shell generalization of the BCJ double copy for amplitudes. I use off-shell here, perhaps slightly incorrectly compared to the way it was used earlier, in the sense of I just mean, you know, what an amplitude is that everything goes off to infinity. If you have a classical field and you want to know what is the classical field at this point, it has a length scale that has a non-zero momentum associated with it if you do the Fourier transform. So, you know, it's, in some sense, you've taken one of your legs away from infinity and brought it into a finite point. So there was early work on that done by this list of people here. And there are possible astrophysical applications of this. The main one, which I've sort of name dropped throughout the entire talk, is the LIGO experiment, which has recently discovered gravitational waves. Typically, these gravitational wave signals come from inspiraling very heavy objects like black holes, or it might be neutron stars, and so on. And there are three phases to any of these processes. So you have a sort of orbital phase where these things orbit around each other, radiate away gravitational waves and get closer to each other. They then merge together to make a single object. And then finally, the thing sort of wobbles and settles down, which is what they call the ring down phase. Now, experimenters basically need very precise predictions for the inspiral phase from classical GR. So the merger phase is typically modeled numerically using numerical GR. those are very complicated calculations to do. What makes them easier to do is if you have more perturbative information from this side that you can feed in to reduce the amount of non-perturbative stuff that you have to do in this phase here. So people are starting to explore getting information for these inspiraling black holes using amplitudes techniques, including the double copy. There's a popular approach for describing gravitational radiation using amplitudes called the KMOC approach, which stands for Kosawa, Maybe, and O'Connell. Recently, corrections to the scattering of spinless binaries was done in what we call the post-Minkowskian expansion. So I only mention that, I think, because this is a case where new information that is needed for these kinds of events was generated from these double copy techniques that went beyond what GR people already knew. And essentially what these double copy methods do is they make those classical GR calculations much, much more efficient because you're really working in a simpler gauge theory and then copying the results to a complicated gravity theory. Also, some people have looked at effective actions, which also enter these methods for looking at spiraling black holes. So these people have looked at dilaton gravity rather than gravity, but shown that you can get it from the double copy. And there's related work, I would say, by these people here. This is now a massive area because of the topicality of gravitational waves. An enormous number of people are jumping on this field, and so yeah, this doesn't even do justice, I think, to the people that are working on this. If anyone does know of any names that I should add, even from your own groups or whatever, then just let me know, and I can add them.
So, sorry, Christopher, if you don't mind my asking, I guess it's a big field, but since you're doing such a wonderful job of giving us this exposure, I mean, what I know about is a kind of post-Newtonian expansion, right? Which is basically in 1 over the speed of light, and you compute the corrections order by order. And is it possible to map just that expansion to a double copy, like, story, so that order by order, it gets more efficient to compute it in the single copy and then double it up, or
yes,
how?
I believe so, because they, what happens, I mean, typically amplitudes are done fully relativistically, so that would be the post-Minkowskian expansion. But to make actual contact with what experimenters need, you do need to consider the post-Newtonian expansion. And I think what typically happens is that you calculate in the amplitude side in an effective field theory, and then so what you obtain finally is in the post-Newtonian expansion, I think, rather than the post-Minkowskian expansion. I would need to look up the details of this, I will be honest. But if I'm sure if we look in this reference, they will be discussing the post-Newtonian expansion and how to match with what experimenters actually need.
I see.
I know that certainly has been discussed. I'm just not working at the forefront of that area enough to be able to.
Sure. Thank you.
Okay. I mean, what I would say is as well, there's now a whole conference every year called QCD Meets Gravity, just devoted to this topic of the double copy, and that's grown. During the pandemic, when people could log in online, it had 250 participants from I think 23 countries when we worked it out. So what I've liked about those meetings, I mean, I was actually one of the organizers of the first meeting, and how it's grown is fantastic. What I noticed at each of those meetings is that more and more astronomers are turning up. So there really does seem to be a dialogue between both sides. As always in physics and how specialized it is nowadays, the language different types of physicists speak is very often the barrier to them being able to talk to each other. So I think the next few years will see us have to get better at telling each other what it is we do. And very often, of course, people are doing the same thing. They just don't realize it.
Thank you.
Okay. So yes, all of the previous examples of the double copy that I've shown you in this talk have been either perturbative, or where they are exact solutions, they happen to linearize the field equations or something. So they're sort of perturbative-ish. So yes, there are various ideas, which I can't do justice to here really, but for going beyond perturbation theory. This is something that fascinates me a lot. Not necessarily other people, but I want to know that picture that I showed you of the double copy and that ladder of theories. I pose that question: how general is this? Is this true for the complete theories in some sense? In which case, it should be true non-perturbatively, whatever that means. And given that we don't have, there's many non-perturbative quantum things we don't know about in gauge theory, let alone in gravity. So it'd be very exciting to find a genuine non-perturbative quantum-like object that maps between the theories. Anyway, some ideas for looking at non-perturbative stuff are listed here. You may be able to think of more. So first of all, given that by adjoint field theory is somehow the simplest theory in that ladder of theories. What no one had really thought of doing until recently was saying, well, why don't we just look for some non-perturbative solutions of that theory, you know, some non-linear, one of the coupling-like solutions. Now, what I would say is for anyone that knows about solitons and things, there's absolutely easy pickings to be had here. So we've had a series of papers where we've derived some interesting solutions which look like monopoles and things in bialgebroic theory, and we've tried to match them up with gauge theory, unsuccessfully, I may add. You can also take symmetries in gauge theory and match them up with gravity theories. There's been some nice work looking at electromagnetic duality, which relates, you know, electrical magnetic fields in gauge theory, and saying what is the gravitational counterpart, and that is known. What about looking at topological information and whether that copies? So certain topological information does. And you can also look at alternative theories where things are just much clearer. So if you go to 2 dimensions, there are certain exotic theories where the double copy is manifest at the level of the Lagrangian. If you look at the self-dual sector in Yang-Mills and gravity, the same is true, and so on. So there we get a really nice understanding actually of BCJ duality and how that relates to classical fields and so on. So what I would say is there's potentially lots to be done here, but new and clever ideas are needed. And this is very much still a field where, you know, in some, certainly on the non-perturbative side, not a lot has been done. So people coming in with a fresh pair of eyes can really have some new ideas and so on. So yeah, if anyone ever wants to get in touch to discuss possible things, then please do. So in that case, let me conclude. The double copy is a widely studied relationship between scattering amplitudes, but classical solutions obey a related double copy. Exact statements are possible, but we can also work perturbatively if we need to. Astrophysical applications are starting to be explored, and the non-perturbative understanding of this thing is still in its infancy, but there are some tantalizing hints of interesting non-perturbative structures between different theories. So I've said here, new ideas are welcome from at least HEP-TH, HEP-PH, AstroPH, and GRQC. I could have added Math-PH as well, and the list of archive classifications is ever growing. So yes, so yeah, I hope that was a nice overview, and I'll leave it there. Thanks.
Let's unmute ourselves and thank Christopher for a very nice talk.
Thank you.
Are there questions?
Sir, I have a question. Am I audible?
Yes.
Yes, sir. If for Hawking radiation, for Hawking radiation, we'll need some kind of deviation from the background curvature to have some kind of particles coming out of vacuum, which might follow some other kind of which will follow some other kind of gauge theory. So what kind of double copy explanation could we have to that?
Hello.
Am I audible, sir?
Hi, Chris, can you hear us?
Yes, I can, but that question I didn't hear very well, I'm afraid, because the connection kept moving.
Yes, sir. Sir, for Hawking radiation, we need to, for Hawking radiation or undue radiation in general, we need to have some kind of change in the gravitational field, which of the curvature over some background curvature. So for particles coming out of vacuum, which follows certain kind of gauge theory, what kind of double copy explanation could we have to that from the gravity side and the gauge side? Because
yes, I'm not sure I'm going to be able to answer your question, but it's a good one. So I get asked about Hawking radiation a lot. I also get asked about the Bekenstein-Hawking entropy as well, which involves similar issues. Now, of course, on the gravity side, you have a physical horizon. You know, you have a distance that is picked out on the gravity side, and it's because, you know, there's no such thing as a zero metric on the gravity side. You always have the Minkowski metric plus the graviton, and it's really kind of the interplay between those two that gives you the horizon. On the gauge theory side, you have no horizon, but I've wondered for some years whether it's possible to cut out an arbitrary radius in the gauge theory such that you can associate some sort of gauge theory like single copy of Hawking radiation and or entropy with that surface. I've never gone much further with that. Some people I think have. I think J.J. Carrasco had an idea that you could have electric fields when you get near a point charge that become sufficiently strong that you would get Schwinger pair production. And then that would look like a sort of gauge theory analog of Hawking radiation. But I don't know whether he ever made that concrete. I don't think I'm answering your question, but maybe I'm saying some relevant things. What I would say is, if you think there's something to think about there, I would strongly encourage you to think about it.
Okay, thank you, sir.
So maybe actually that's the answer you want, is that no, it hasn't been done, and there's possibly a paper in it.
Thank you, sir.
Hello. Yeah. Can I ask a question? Yeah.
Yep.
Yeah. So when you talked about this wild double copy, you had this you took the solution from gauge theory, FAB and FA prime B prime, and you constructed the wild tensor.
That's right.
So on the gravity side, you have some conformal gravity theory or like normal Einstein gravity, because you are constructing wild tensor.
Yes, although for vacuum solutions, the Riemann tensor reduces to the Wahl tensor. So because I was talking about vacuum solutions only, it didn't matter that I was only talking about the Wahl spinner. For solutions where you had sources as well, it would have to be more complicated.
Okay, because okay, so from the Wild tensor, now if you want to reconstruct the metric, you always have this scale transformation that you can do, right? Because Wild tensor is scale invariant.
Yeah.
So if you can only reconstruct a metric up to some overall scaling, right?
Yes, and I was saying that something like the classical double copy has to be true for general conformally flat spacetimes.
Mm-hmm.
That's overlapping with what you're saying, right? In that something for vacuum cases, something like that Wahl double copy will be true for arbitrary conformally flat spacetimes, which are related by just a conformal scaling of the metric, I think.
Okay. So here you are like, so the Wild tensor that you're constructing, it's a solution of what, like what equations?
It's a solution of the massless free field equation.
Of which theory? Conformal gravity or?
Of Einstein gravity.
Einstein gravity.
So yeah, where is it? It solves this thing basically.
Okay.
But that equation is also conformally invariant.
Conformally invariant, right? Yeah.
So it's not inconsistent with what you're saying, I think.
Okay. Okay, thanks.
Hi, can I ask?
Yeah, go
or somebody else asking. Hi, Christopher. That was a very nice talk. So my question is about the fact that well, we know that we can write gravity as a gauge theory, right? I mean, we have a formalism to do that.
The Ashtekar variable.
That's right. The Ashtekar variables.
Yeah.
And like, doesn't that already tell us that gravity is a gauge theory, or why is it that people don't consider that when they talk about?
I've puzzled about this because the what that framework does for us is tell us that gravity is like a gauge theory. However, of course, what the double copy is saying is that certain structures in the non-abelian gauge theory occur twice in the gravity theory. So it's a different statement. But I have often wondered whether, if one looked at alternative formulations of gravity, whether they would be more natural for looking at the double copy in. However, the key point about the double copy is, in some sense, gravity is like two bits of a gauge theory put together rather than a single gauge theory. So on the face of it, it's a different statement. But I do wonder whether methods, different formalisms for gravity, things like the Ashtekar variables, may shed light on some of these topics. I haven't looked at that myself because I don't know enough about it, but yeah, I think there may well be something to look at there. The key point here is not to show that gravity is a gauge theory, that we know already. It's to somehow show that structures that are in a non-abelian gauge theory are also sitting there in a gravity theory. So in a sense, structures or methods from gauge theory can be recycled to gravity. So the emphasis is somewhat different. But looking at different formalisms for gravity may make some of these issues clearer, perhaps.
Okay, thanks.
There's a raised hand by Shivam. Shivam, please ask your question.
Okay, thank you. So my question is related to the Schwarzschild metric. We saw that how Schwarzschild solution is related to point charge potential due to a point charge in the gauge theory. So, but that's all stationary situations. If you take some time-dependent situation, for example, where the geometry is in gravity, does it mean that we have a potential due to some in vacuum is suddenly changing to a potential due to point charge?
Yes, so for time dependence, some cases have been looked at. The case of, I mean, the two extreme cases, if you like, something not moving at all, which I told you about here, and something moving at the speed of light. And that would be a plane wave or a shock wave or something like that. So we do know that shock waves double copy, but that's almost like a trivial time dependence again, because it's the fastest you can go rather than the slowest you can go. What I would say is that Mariana Gonzalez and collaborators, I think, looked at generalizing the stationary case to if you have arbitrary killing vectors, not just one in the time direction.
Okay.
So there is a bit of literature on time dependence, but I'm sure there's more to be done there.
But for example, I mean, the particular example I was talking about, have you looked at this Vaidya kind of geometries where in the geometry we have the black hole formation?
I presume that's one of these types of geometry where we wouldn't know how to double copy it because it wasn't type D. So I think no one has looked at that actually. Whether there's sort of test cases that can be done, I don't know. I mean, it's interesting what you're saying. I just don't know the answer.
Okay. Yeah. Okay. Thanks.
Can I ask a question? Thanks for the nice talk, Chris. So you give an overview of various things, and I was wondering if you could tell us a little bit about this fact that when we do the double copy usually for Yang-Mills, you don't just get out the graviton, right? You also get out the axion and dilaton.
Yes.
So what has been the progress on that, on trying to trying to remove the contributions of axions and dilatons if you wanted just gravity answers?
Very good. Yeah, I completely skimmed over that. So you're quite correct to pull me up on it. So for most of the classical solutions I talked about, which were at linear level only, this is never a problem because you can choose from your external polarization vectors or whatever that these states are not turned on. Where it does matter though is in amplitudes, because even if you're calculating only classical things in GR, you do that by coupling. You get loop diagrams, which parts of which is classical. So then you have to worry about things running around the loops. There were some ideas for this. The best one I saw was by Otteroff and Johansson a couple of years ago, where they introduced ghosts, not in any traditional sense, but they put extra scalar degrees of freedom in the gauge theory, such that when you double copied them, you put in a minus sign by hand. So these were ghosts sort of under the double copy, very different to any other kind of ghost, and maybe even the word ghost is not appropriate. But that actually did work in systematically removing, at least at one loop level, the axion and the dilaton. Quite what these people are doing, that are doing these 3-loop calculations for the GR people, I don't know, but I would imagine because they're using generalized unitarity methods, so that they only have, they can choose the external states that they bolt together to make the gravity amplitude. So it may be that they're able to very precisely control what runs around their loops. But I would have to check their papers to know exactly what they're doing.
Yeah, I was wondering specifically for those kind of post-Minkowskian.
Because they've gone up to 3-loop level. So I would need to delve into their paper to see what they've done there. They will have an answer to it, I think. Yeah. I should say, unfortunately, I have to leave in a couple of minutes because I've got another meeting, if that's all right. But
okay, I just ask one more question, if it's okay. So you had in a couple of years ago, you had written this review article where you were saying that maybe the double copy shows up in quantum optics experiments where they're trying to model gravitational waves going through curved spacetimes by using some electromagnetic waves moving in some material. And you were expressing hope that maybe that also gives us some insights to how the double copy works. You could have information transfer, so to say. did that go anywhere? Do you know if anything?
Well, sort of, but yeah. Okay, so let me explain what the idea was. So there was a Nature paper a few years ago, just by optics people, basically saying if you look at entangled pairs of photons, you can simulate a graviton. And then they said, oh, but you get these two combinations of polarization states that we don't know what they are, so we just throw them away. Now, those are the axion and the dilaton.
Mm-hmm.
So, you know, what they had done without realizing it was the double copy at linearized level. And one of the open questions we have is, does that double copy work arbitrarily for arbitrary curved backgrounds?
Right.
So it seems to me you could entangle these things to make simulated gravitons, axion, and dilatons, put them through a fiber optic cable to simulate a curved background, and that might tell you something about the double copying curved backgrounds. It's rather tenuous, but I mean, I at least I'm in contact with, I used to work as a lecturer at Glasgow in Scotland here in the UK, and they are specialists on optics. They have a quantum optics lab, and they were offering to entangle some photons and pass them through a fiber optic cable. And then at the very least, we could show that, you know, they said that if you send a beam with spin around a loop in this fiber optic cable, the polarization vector rotates. So it seems to me one simple thing we can do, just to see that the double copy works, is to make the axion the dilaton and what we think is the graviton, and show that in one case the spin vector rotates, and in the other case nothing happens because they should be scalar degrees of freedom. I'm not sure that tells us much about the double copy, but it would be kind of fun just to put the double copy on a tabletop.
Yeah. I felt this is one of those rare cases where maybe we have some experiments where.
Yeah, I mean, going to nonlinear effects is difficult because you would be having to simulate gravitational nonlinearities using nonlinear optics.
Right.
But the trouble with nonlinear optics is just you hardly ever get fields that strong. It's just very difficult to do nonlinear optics because, the electromagnetic structure constant is so small. So that I don't know what would be explorable, but I thought at least the proof of principle that you could simulate things on a tabletop would be worth doing.
Right.
So yeah, I should chase up these people in Glasgow, I think. I'm afraid I really do have to go because I've got
sure. Thanks a lot for the talk.
Thanks a lot.
Well, look, thank you. And this has been one of the most enjoyable seminars I've ever given because of all your amazing questions. So absolutely brilliant. If you've got any more questions at all, or any of you just want to, have a chat or something about what to work on, please do get in touch.
Sure. Okay.
Okay, thanks. Have a nice evening, guys. Yep. Okay.
Bye.